Welcome to Calculus. Today we will determine if a given function is continuous or not. If the function is discontinuous, we will locate and classify the discontinuity, then describe the intervals over which the function is continuous. Let's take a look at one example to begin, which we'll take a look at really after we define three different types of discontinuity. Let's head over to our notes screen. So I've got these three different kinds of discontinuity listed here, and let's just take a moment to define what is a jump discontinuity, an infinite discontinuity, or a removable discontinuity. So we'll give the definition in words first, and then I'd like to just sketch a quick example here on the side. So we'll start with a jump discontinuity. So a function is said to have a jump discontinuity. A function has a jump discontinuity if the left-hand limit, so we're talking about the side where we're coming from the left-hand limit and the right-hand limit. So again, we're just thinking about limits, one from the left, one from the right, are both finite, but not equal. So there's a written definition of a jump discontinuity. So if the left-hand limit and the right-hand limit are both finite, which means they come to a certain number in the y values, but those y values aren't the same numbers. Let's sketch an example here over to the side. A lot of times a picture is worth 1,000 words. So let's say we have a function that's kind of a quadratic function that's beginning here in quadrant 2 and swinging down through 3 and 4. And then we're going to make the claim that it is restricted on its domain. So we're going to end that parabola there on the right. So this is going to be a piecewise function. And let's say that we pick up with a linear function that starts at the same x value, but a y value above that parabola, and then from that y value veers off to the right. So note here that these two spots, this x value, the limit from the left is finite, so it ends at a certain x and y value, and the limit from the right ends at a certain x and y value, but they aren't the same y values. There's a gap in the graph. It's like we would have to, if we were to get from the parabola to the line, we would have to jump. So that's a jump discontinuity. Let's compare that to an infinite discontinuity. So you'll notice as we write a word description of infinite discontinuity, pretty much everything's the same. So see if you can predict what's different, do you think, with an infinite discontinuity from a jump discontinuity. So a function has an infinite discontinuity. A lot of times this is also called an essential discontinuity if the left-hand limit and the right-hand limit are both. And how would you change that description from the jump discontinuity? In the jump discontinuity, it was finite. The clue here is in the name, are both infinite. And really, we don't have to restrict that to both limits from the left and from the right being infinite. It could be that just one is infinite, or both infinite, or one is infinite. So let's sketch an example here as well. And really, we got to ask about equality. Can infinity be equal to infinity? It's hard to say. That's not a definite term. Like infinity is a moving number. Well, let's sketch a graph so we can see it. So something like this, if I had a rational function that had a vertical asymptote, and let's say that this left-hand branch, as it approached a certain x value, went to positive infinity from the left, whereas from the right, if we were to approach that same x value, it went to negative infinity. A lot of rational functions show that behavior. Well, definitely in this case, those values are not the same. One's going up towards the heavens infinitely. One's going down towards the earth infinitely. So even in that case, we can see they're not equal. But what's different from an infinite discontinuity to a jump discontinuity is that the y values are infinite, at least one side. Well, that will contrast with what we'll see here with a removable discontinuity. So again, we're going to start with our word definition. A function has a removable discontinuity. So here we're going to see a combination of the things that we've said for jump and infinite discontinuity. So it has a removable discontinuity if the left-hand limit and the right-hand limit are both finite. So that's something we're taking from the jump discontinuity. And surprisingly enough, equal. But not equal to the function at that point. But not equal to the function at that point. So note how we're taking parts from these different definitions to finalize this removable discontinuity definition. So again, there's our words. And let's fill in with a graph that can just serve as an example of a removable discontinuity. So here's a coordinate plane. So let's say we've got another parabola. This one's upside down. But at a certain x value, there's a gap in the graph. And that happens when you got a rational function where something cancels above and below. But everything else on that parabola is as usual. And then let's just say that the function includes a piecewise portion where this x value is defined at a y value not on that curve. So again, what we're saying with our definition is the left-hand limit is finite, comes to a certain y value over there. The right-hand limit's also finite, and they are equal. They're coming to the same y value. But the function value is not equal to that y value at that x value. That is what we call a removable discontinuity. So those are our three definitions with some examples just to illustrate them. Oh, I see I made a mistake here. Let me fix it. So a function has an infinite discontinuity. Okay, so make sure I get my verb in place. Well, let's take a look at one example to begin where we have to determine, is the function continuous? Is it discontinuous? And if it's discontinuous, what kind? So I've got here the function f of x equals negative x plus 2 in my numerator over x squared plus x minus 2 in the denominator. So I want to start off by really just looking at the function and graphing it. So here I'm going to create a t-chart like we've done. And a lot of times a t-chart's very useful for investigating limits. It's also very useful to sketch a graph. Now, over here to the side, one thing that I want to do is I want to take this function and see if I can factor the denominator. I'm just going to write the numerator as is because it's already a linear factor, x plus 2. But that denominator, x squared plus x minus 2, I want to come up with two linear factors that would be equivalent to that quadratic trinomial. So I see x and x would multiply to give x squared. So then I need to come up with two numbers that multiply to -2, that's that c term, and add up to 1. That's the kind of the understood coefficient on x. So I need two numbers that multiply to -2, add to +1. So I think what we're looking at is +2 and -1. So let's just check, see if it does it. So 2 times -1 is -2. That checks out. 2 plus -1 is +1. Now I'm going to take those values and write them in the denominator. So that's x plus 2, that's x minus 1. Now take a moment to look at that fraction, and what do you notice when you compare the numerator and the denominator? Excellent. We have a term that is identical above and below. So x plus 2 features in both the numerator and the denominator. And what we can say algebraically is if I've got something divided by itself, it will cancel and leave 1. Now that is basically a hole in the graph or a gap in the graph. So what I'm going to do is I'm going to take that x plus 2, and although it's canceling out, I do need to take into account that that is in the denominator and it cannot equal 0. Because if I have a 0 right here, it's going to be 0 times something will be 0, and then I'll be trying to have a division by 0. And again, that's not algebraically sound. So I'm going to solve this really anti-equation. So I'm going to subtract 2. So what we're saying is that x cannot equal -2. We're just going to hold on to that fact. Now I'm going to graph something here that is from the reduced form of this rational function after we canceled out that x plus 2 term. So we're going to just leave 1 in the numerator over x minus 1. So I'm going to create my t-chart based on that simplified function. So let's take -2 through 2. Again, we choose those values very frequently because they center our domain around the origin. And let's calculate these outputs. So I'm going to calculate f at -2. So I'm just going to take that -2 in this simplified version. I'm going to plug it in for x. So it's -1 over x minus -2. And that's going to reduce down to -1 over, I did that incorrectly. Let me correct that. I got carried away with the algebra. -2 should go where x is. So that's -2 minus 1. So that's corrected. That's -3. So that's an output of 1/3. So we've got this point here, -2, 1/3. All right, so let's keep going. F at -1. Again, I'm taking that simplified version, so -1 over, I'm replacing x with that specific value, -1 minus 1. So that's -1. I'm going to erase the word gap. -1 over -2, which is 1/2. So we've also got the point -1, 1/2. So that left-hand side, it starts to raise up off the x-axis. Half is bigger than a third. F at 0 is -1 over, replace x with 0, -1, which is -1 over -1, or +1. So we see that pattern continuing. As I get right on the y-axis there, I'm up at the y-intercept of 0, 1. Let's calculate when x is +1. So that's -1 over 1 minus 1. And I see immediately I'm running into a problem. So this is -1. Let's kind of make some room for ourselves here. That's -1 over 1 minus 1 is 0. And that, what we would say, is undefined. Now let's keep on going. So I think that that's a vertical asymptote on the graph. Let's calculate though at +2. We may have to go to 3 as well just to get a good snapshot of the function. So I'm going to put in 2. So -1 over 2 minus 1 is -1 over 1, which is -1. So this is showing that asymptotal behavior where the second branch is on the lower side of the x-axis. So we've got the point 2, -1. And let's just calculate if x was 3 very quickly. So f at 3 equals -1 over 3 minus 1, excuse me, which is -1 over 2. So that's the point 3, -1/2. Based on the pattern there, I would say that for 4, it's probably -1/3, since we've got a symmetry going on. Same numbers, different signs. Well, let's graph this function. So I'm going to graph those points. -2 1/3 is roughly there. Let me not make that point too large. -1 is at half. 0, again, we said was at 1. And then we believe that there is a vertical asymptote here at the x value of +1. And again, I see that because it's undefined at that point. I'm trying to divide by 0. At 2, I'm at -1. At 3, I'm at -1/2. And then 4, I had predicted, hey, that's at -1/3. Now, I believe that we also have a horizontal asymptote at the x-axis. And so as I place that graph here on the coordinate plane, this left side is there on the x-axis and then hugs that vertical line at +1. And then that lower right-hand branch of the rational function starts at the lower part of that vertical asymptote and then goes to the right along the lower side of the x-axis. So definitely we've got one discontinuity here that's represented by this undefined term. Now, if I compare that back with, so we'll look back in a second at those 3 descriptions of the jump, the infinite, and the removable discontinuity. But before I forget, we had done some work initially to cancel a value, and that with the x + 2 above and below, I got to find that here on my graph. Let me create that gap, and then what we'll do is we'll say, is that another discontinuity? So I'm going to put this, I'll put it in green. There's a little gap in the graph at -2. So anytime you have a factor cancel above and below, it doesn't give you an asymptote, but it gives you what we call kind of a hole or a gap in the graph. So really, I've got 2 discontinuities. That's a nice one. So I'm going to go up here. Let's start, in fact, with this gap in the graph. And really what I need to see is which one of these three descriptions does that gap most match. So is it a jump discontinuity where the y values are different from the left and from the right? Or is it an infinite discontinuity where they're going in opposite directions or maybe going infinitely in one direction? Or is it a finite limit from the left and a finite limit from the right coming to the same y value? So is it jump? Is it infinite? Is it removable? Well, it looks to me like this is the left-hand side of the function f of x as it approaches -2 is coming to the same y value as the right-hand limit of the same function. So how would you classify that? Excellent. That is a removable discontinuity. They're finite and they're equal, but the function doesn't have that y value in its original range. It's a removable discontinuity. Basically, it's a gap or a hole in the graph. Well, that takes care of that one discontinuity, but we did have another one. So this vertical asymptote, which we saw in our table as an undefined term, again, if I look back at my examples, it's not removable because they're not coming to the same y value. One side of the graph's going up, one side's going down, and it looks like what we've got going on is an infinite discontinuity. And for sure, that's classic infinite discontinuity. So in some functions, you can have multiple discontinuities, places in the graph where the y values don't equal each other as the x values go from one to the next. So this is an infinite discontinuity. Well, that gives us one example really with two kinds of these discontinuities. We'll pause at this moment to give you a chance to work on some of your questions and your graphs and functions. And as you go, make sure that you just write, give me a table. If you've got some cancellation, show that algebra, and then give a graph and draw in the discontinuities. And then if you'll label the type of discontinuity that you see. Of course, it may be continuous. So have your eyes open for something that is totally smooth and connected across its domain. So thank you for joining for this first example. We'll return in just a moment with two more examples. See you soon.